Hi folks, we're going to take a look at solving rational inequalities now. So in the last video we saw how to solve a polynomial inequality. So say you have 2x cubed minus 4 and you want to determine when that's greater than or equal to x squared minus x. Okay. The way in which we solve that is we said, well, it's very easy to determine when a polynomial is greater than or equal to 0. So we brought all terms to one side of the equation. Okay, and again, we had a problem that involved just determining the x-intercepts of a polynomial. So if you could determine the factors of this polynomial, okay, we realized, hey, those x-intercepts will be the only places where the polynomial can change sign. Okay, so it's just a matter of testing one point in each of those intervals, and we could do that by quickly graphing the function. Okay, so we'd graph the function, and from there we can just read off the graph where it's greater than or equal to 0. Okay, so the question is can we apply our methods for solving a rational equation to solving a rational inequality? Okay, now if this was a rational equation, so if this was an equal sign here, the way in which we would solve this is to just get rid of those denominators by multiplying both sides of the equation by t plus 1 and t plus 8. And then we would generate a polynomial equation and solve it that way. Unfortunately, there's a big problem now when we're dealing with a rational inequality. Okay, let's say I multiply both sides by t plus 1. The problem is sometimes t plus 1 is positive and sometimes it's negative. And of course, when we multiply both sides of an inequality by a negative number, we saw that we have to change the direction of the inequality. So that means we'd have to split up this problem into two parts. Solve it where t plus 1 is greater than 0, solve it where t plus 1 is less than 0. But then in each of those cases we're also multiplying both sides of the equation with by t plus 8, which could also be positive or negative. So now for each of those two cases you're going to have to split it up into two cases again, depending on whether t plus 8 is greater than or equal to 0. So we can see that it can get very complex very quickly. Okay, but let's remember that we had an alternative method for solving rational equations, okay, which I think is now going to come in handy. And the idea here is not to multiply any variable terms to each side of the equation, but do something similar to what we did with polynomials, which is bring everything to one side of the equation, okay, and write that side as a single rational expression, and then have that greater than or less than, or in this case here, greater than or equal to 0. Okay, and then from there we'll see where we go. Although as I'm doing the algebra, you might start to think about how I'm going to use this single rational expression to solve my problem. Okay, so here we have to subtract these using common denominators. So here we have 20t times, well, we're missing the t plus 8, so t plus 8, okay, minus 240 times, here we're missing the t plus 1, so multiply 240 by t plus 1, okay, and all over our common denominator. Okay, so now we simplify this here, so what do we have? We have 20t squared plus 160t minus 240t minus 240. Okay, and so finally at the top we have 20t squared minus 80t minus 240 all over t plus 1 times t plus 8. Okay, and so now what we have is we have a single rational expression greater than or equal to 0. Okay, and again we use a similar idea as we did with our polynomial equations, is we know that this expression can only change its sign at certain t values. Okay, it can only change sign again at x-intercepts, but it can also change sign at a vertical asymptote, possibly a hole. Okay, so if we can determine those locations where it can change sign, similar to what we did before, it's just a matter of testing each interval and reading off that where it's going to be greater than or equal to 0. Okay, so in order to determine here, we can easily see where the vertical asymptotes are going to be located. Let's factor the numerator to see where the x-intercepts are and see if there's any holes that are going to be generated. So here, to make my life easier, I'll start by factoring out the 20. Okay, so here minus 4t, and here we've got minus 12. Okay, so t plus 1, t plus 8. And lastly, that looks like it's an easy factorization, so t minus 6, t plus 2. Okay, and so now all we have to do is create a chart, and I'm going to do that actually by using just a number line, okay, to help me determine where this expression is positive or negative. So the only places it can change sign is, well, at the vertical asymptote of negative 8, okay, at the x-intercept of negative 2, at the vertical asymptote of negative 1, and at the x-intercept of 6. Okay, so again, notice how I don't make any effort to be consistent with my number line, because all I care about is where it's positive and where it's negative. Now, one thing I want to mention here, if you notice, I used open circles for negative 8 and negative 1, and I used closed circles for negative 2 and 6. Okay, it's a trick I'd like to suggest, because here, because there's vertical asymptotes at these points here, you can never include negative 8 and negative 1 in your solutions, okay, because this expression doesn't exist at those t values. So, there's no point in considering whether they're greater than or equal to 0. Whereas at the x-intercepts, because it's greater than or equal to 0, I know that I want to include those numbers in my solution, because when when t is equal to negative 2, this expression is going to be equal to 0. Whereas if there was no equal sign here, I would have also put open circles around those. It's just so that at the end I don't actually have to think about, whether I'm including the points, and sometimes people accidentally include the vertical asymptotes as soon as they see an equal sign. So this is one way to avoid mistakes. And so now we're going to determine the sign in the same way that we did when we were sketching rational functions. So again, sketching the function itself isn't too easy. So what we're going to do is we're going to test one value in each interval, and we know that if it's positive or negative in that interval, it's going to have to be positive and negative everywhere in that interval. So here, let's say I take negative 9. Okay, so let's say I pick negative 9. So here, I realize this is negative, negative. So I have a positive in the numerator, and this is going to be negative, and again negative, so positive in the denominator. So it has to be positive in that interval. So here, let's say we pick negative 3. Okay, so we've got negative and negative. So again, positive in the numerator. But here, negative 3 plus 1 is negative, but negative 3 plus 8 is positive. So negative times positive is negative, so negative in that interval. Here, let's take negative 1.5. Okay, so here, negative positive, so negative in the numerator. Okay, and here we have, again, negative positive, so negative in the denominator, so positive there. Here, let's stick in 0. Okay, so negative positive, and here positive positive, so altogether negative. And then here let's take a 7. Okay, and here we realize that we've got positive, 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 positive. Okay, and so now I can read my answer straight from this number line. So when is this expression greater than or equal to 0? Well, from negative infinity to 8. Okay, and again, to negative 8, and here I see my open circle, it's a vertical asymptote, I don't want to include negative 8. Okay, then I see that it's also positive between negative 2 and negative 1. Okay, but here I want to include negative 2, so I use square brackets, but I don't want to include negative 1. And then I see that it's greater than 0 from 6 onward. So from 6, and again, I want to use a square bracket because I want to include 6, okay, to positive infinity. Okay, and since it's all these sets together that make up my solution, let's remember what that symbol is to unite all these sets, as we use the union symbol. Okay, so let's just do a quick recap. So number one, when you're solving a rational inequality, you do not, under any circumstance, want to multiply or divide both sides by anything that contains a variable, where it can sometimes be positive, sometimes be negative. Okay, if it's just a constant, it's fine, and just deal with it as needed, but never when you have a variable expression. Okay, so the alternative to that is to bring all terms to one side of the equation and then write it as a single rational expression. Okay, factor to get all the x-intercepts, vertical asymptotes, possibly holes for that expression that's left over, and then from there use our trick of testing the sign of one value in each of the intervals created by the x-intercepts and the vertical asymptotes. And then from there, just read your answer off the